Welcome! In this session, we'll explore an exciting problem titled Next Greater Numerically Balanced Number. We'll discuss the problem, break it down into manageable parts, and analyze different approaches to solve it effectively. Let's dive in. To tackle the problem of finding the next numerically balanced number, we can start by considering a brute force approach. The intuition here is straightforward. We incrementally check every number greater than the given input n until we find one that satisfies the numerically balanced property. A number is considered numerically balanced if, for each digit it contains, the digit's frequency matches its value. For instance, the number 22 is numerically balanced because the digit 2 appears exactly 2 times. The steps for this approach involve incrementing n to generate candidates, counting the frequency of each digit in the candidate, and verifying whether the frequency matches the digit itself. If a number satisfies this condition, we return it, otherwise, we keep searching. However, this method has significant drawbacks. Its time complexity is k*m, where k is the number of candidates checked and m is the number of digits in each candidate. This inefficiency arises because we might need to check a large number of candidates, especially for larger input values, making this approach computationally expensive. Now, to address the inefficiencies of the brute force approach, we can consider an optimized approach that reduces the search space and eliminates unnecessary checks. The key idea here is to leverage the structured nature of numerically balanced numbers. Instead of iterating through all possible numbers, we pre-compute all numerically balanced numbers up to a reasonable limit, such as 10 to the power of 6. This involves generating valid combinations of digits that satisfy the numerically balanced property. Once pre-computed, we sort these numbers and use a binary search to quickly locate the smallest number greater than n. This method is far more efficient because numerically balanced numbers are relatively rare, meaning the pre-computed list is small and manageable. Additionally, the constraints of this problem allow pre-computation without exhausting memory resources. The time complexity of this approach is efficient as well. Pre-computation is a one-time cost that enables near-instant lookups in subsequent queries. Binary search, for example, operates in O log p, where p is the size of the pre-computed list. This method is both efficient and scalable within the given constraints. While the optimized approach significantly reduces runtime, it does come with some trade-offs. One drawback is the additional memory required to store the pre-computed list of numerically balanced numbers, which could be a consideration for environments with limited resources. Furthermore, the pre-computation step is specific to a certain range, such as up to 10 to the power of 6, and may not generalize to problems with larger input limits unless the range is extended. Despite these trade-offs, the optimized approach is the preferred strategy for this problem because it achieves a balance between efficiency and scalability. The brute force method, while simpler to implement, is computationally impractical for larger inputs due to its high time complexity. By pre-computing numerically balanced numbers, we achieve near constant time lookups after the initial setup, which is a significant advantage. In summary, the optimized approach stands out for its ability to handle the problem efficiently within the given constraints, making it the best choice for this scenario. To start, let's define what it means for a number to be numerically balanced. A number is numerically balanced if, for each digit in the number, the digit appears exactly as many times as its value. For example, 22 is balanced because the digit 2 appears exactly 2 times. Similarly, 1333 is balanced because the digit 1 appears 1 time, and the digit 3 appears 3 times. The task is to find the smallest numerically balanced number that is greater than a given number, n. To approach this, we can start with a brute force method. This involves iterating through numbers starting at n+1 and checking each one to see if it satisfies the balance condition. To determine whether a number is balanced, we can first convert it to a string to analyze its digits. Then, we use a frequency counter, such as a dictionary, to compute how many times each digit appears in the number. Finally, we validate whether the frequency of each digit matches its value. If the condition is satisfied for all digits, the number is balanced. Once we have a function to check if a number is balanced, we can use it in the search for the next numerically balanced number. Starting from n+1, we evaluate each candidate number. If a candidate is balanced, we return it and stop the search. While this brute force approach is straightforward, it can become computationally expensive for large numbers. To optimize, we can skip certain invalid numbers. For instance, any number containing digits greater than 9 can never be balanced. Similarly, we can leverage constraints on the digit count, such as the fact that the frequency of a digit cannot exceed its value. For example, the number 111 is invalid because it implies 3 ones, which violates the balance condition for the digit 1. Additionally, we can implement an early exit strategy to stop checking a number as soon as any digit fails the balance condition. These insights significantly reduce the search space and improve efficiency. Balanced numbers are relatively rare, so skipping invalid candidates helps avoid unnecessary computations. Although the brute force method is simple to implement, it is not efficient for larger values of n. Generating balanced numbers directly, rather than iterating through all candidates, could be a more advanced and optimized approach. To support our algorithm, we use specific data structures. A frequency counter, such as a dictionary, allows us to count how often each digit appears in constant time for lookups and updates. This makes the balance check efficient, with a complexity of O(k), where k is the number of digits in the number. Additionally, converting the number to a string simplifies digit extraction and avoids manual arithmetic operations. The algorithm can be summarized in pseudocode. First, we define a function, is_balanced, to check if a given number meets the balance condition. This involves converting the number to a string, counting digit frequencies, and validating that the frequency of each digit matches its value. Then, in the main function, next_balanced_number, we start from n+1 and incrementally check candidates until we find the next balanced number. The main function continues to iterate through candidates, checking each one using the is_balanced function. If a candidate meets the balance condition, it is returned as the result. Otherwise, the candidate is increment, and the loop continues. In terms of complexity, the time required to check balance for a number with k digits is O(k). In the worst case, the loop may iterate through m numbers until a balanced one is found, leading to a total complexity of O(m*k). The space complexity is O(k) due to the frequency counter. Several edge cases need to be considered. For small values of n, such as 0 or 1, the algorithm must handle these correctly since the search begins at n+1. For large values of n, the algorithm should avoid overflow and excessive runtime. Lastly, numbers with digits greater than 9 are inherently invalid, as these cannot meet the balance condition. Handling these scenarios ensures the algorithm is robust and produces accurate results across a wide range of inputs. The solution begins by defining a helper function is_numerically_balanced that determines if a given number is numerically balanced. This function converts the number into a string, counts the frequency of each digit using Python's counter, and checks if each digit matches its frequency. If all digits satisfy this condition, the function returns true, otherwise, it returns false. The main function, nextBeautifulNumber, starts with the number just greater than the input n, i.e., n+1. It then enters a loop, incrementing the current number by 1 in each iteration. For every number, it checks if the number is numerically balanced using the helper function. As soon as it finds a balanced number, it returns that number and exits the loop. This implementation is straightforward, leveraging string manipulation and the counter class for frequency analysis. It systematically increments numbers from n+1 until the next numerically balanced number is found, ensuring correctness. The time complexity is manageable for small input ranges but can increase for larger values of n due to the sequential nature of the search. Here, we start by defining a helper method called isNumericallyBalanced. This function determines whether a given number is numerically balanced. To achieve this, we use a hash map to store the frequency of each digit in the number. We initialize the map and then iterate through the digits of the number using a while loop. In each iteration, we extract the last digit using the modulo operator, update its count in the map, and then remove the digit by performing integer division. Once we have the frequencies of all digits, we check if each digit appears exactly as many times as its value. This is done by iterating over the entries of the map and comparing the digit to its frequency. If any digit fails this condition, the method returns false. Otherwise, it returns true, indicating that the number is numerically balanced. Now, we define the main method nextBeautifulNumber, which finds the next greater numerically balanced number starting from a given input n. We begin by initializing current to n plus 1, as we want to find the next number after n. Using a while loop, we continuously check if the current number is numerically balanced by calling the isNumericallyBalanced helper method. If the method returns true, we immediately return the current number, as it satisfies the condition. Otherwise, we increment current and continue searching. Additionally, in the main method, we provide an example usage of the solution. Here, the input 1 is passed, and the output is 22, which is the next numerically balanced number after 1. This demonstrates how the code works in practice, though the example usage can be removed when submitting the solution. To solve the problem, we start by taking the input number, which is n equals 1. The first step is to initialize current as n plus 1, so current becomes 2. Next, we check if this number is numerically balanced. To do this, we convert current into a string, giving us 2, and then use collections counter to count the frequency of each digit, resulting in 2, 1. Now, for every digit frequency pair, we verify if the digit equals its frequency. Here, the digit 2 has a frequency of 1, and since 2 is not equal to 1, current equals 2 is not numerically balanced. We then increment current to 3 and repeat the process. For current equals 3, the frequency of the digit 3 is also 1, and since 3 does not equal 1, it is not numerically balanced either. We continue checking subsequent values of current. For current equals 4, 5, 6, 7, 8, 9, and 10, none of these numbers are numerically balanced because the frequency of their digits does not match the digits themselves. When we reach current equals 11, we see that the string representation is 11, and the frequency count is 1, 2. Here, the digit 1 appears twice, but since the digit 1 is not equal to its frequency of 2, it is still not balanced. Finally, when current becomes 22, we find that its string representation is 22 and the frequency count is 2, 2. Now, the digit 2 matches its frequency of 2, so 22 is numerically balanced. Therefore, the next greater numerically balanced number after 1 is 22. Now, let's work through another example where the input is n equals 8. We begin by initializing current as n plus 1, which makes current equals 9. Checking if 9 is numerically balanced, we convert it to a string, resulting in 9, and count the frequency of its digits, giving us 9, 1. The digit 9 has a frequency of 1, and since 9 does not equal 1, it's not numerically balanced. We then increment current to 10 and repeat the process. For current equals 10, the string representation is 10, and the frequency count is 1, 1, 0, 1. The digit 1 has a frequency of 1, which satisfies the condition, but the digit 0 has a frequency of 1, which does not match. Thus, 10 is not numerically balanced either. Continuing the process, we check the next values of current. For current equals 11 and 12, neither is numerically balanced because the frequencies of their digits do not match the digits themselves. However, when current reaches 22, we see that its string representation is 22, and the frequency count is 2, 2. Here, the digit 2 appears twice, and its frequency matches the digit value. Therefore, 22 is numerically balanced. This means the next greater numerically balanced number after 8 is 22. Let's now analyze a third example with n equals 100. As before, we start by initializing current as n plus 1, so current equals 101. To check if 101 is numerically balanced, we convert it to a string, resulting in 101, and count the frequency of its digits, which gives 1, 2, 0, 1. Here, the digit 1 appears twice, but since 1 is not equal to its frequency of 2, the number is not numerically balanced. Incrementing current to 102, we find its string representation is 102, and the frequency count is 1, 1, 0, 1, 2, 1. The digit 1 satisfies the condition, but the digits 0 and 2 do not match their respective frequencies. Thus, 102 is also not numerically balanced. We proceed with further checks. For current equals 111, 122, 202, and 212, none of these numbers are numerically balanced, as the frequencies of their digits do not match the digits themselves. Finally, when current reaches 222, we find that its string representation is 222, and the frequency count is 2, 3. The digit 2 appears 3 times, and since its frequency matches the digit's value, 222 is numerically balanced. Therefore, the next greater numerically balanced number after 100 is 222. To analyze the time complexity of our solution, we begin by breaking it into two main components, the is_numerically_balanced function and the next beautiful number function. For is_numerically_balanced, the process involves converting the number to a string, which takes time proportional to the number of digits, or OD. Then, we calculate the frequency of each digit using the counter function, which also operates in OD. Finally, we iterate through the frequency dictionary, which has a maximum of 10 entries since there are only 10 possible digits. This step is constant time, O1. Combining these steps, the overall complexity of is_numerically_balanced is OD. Now, for next beautiful number, the function starts at n+1 and iteratively checks each number to determine if it is numerically balanced. For each number, it calls is_numerically_balanced, which is OD. Let's define m as the next numerically balanced number after n. In the worst case, the function may need to iterate through all numbers between n+1 and m, performing OD work for each. The growth of m is exponential in the number of digits, which means the number of iterations depends largely on the gap between n and m. If we let k represent the number of digits in n, the number of iterations can be proportional to the range of numbers with k digits, which is 10 to the power of k. Since each iteration involves work proportional to the number of digits, or k, the overall time complexity becomes 10 to the power of k asterisk k. Shifting focus to space complexity, the is_numerically_balanced function requires space for the counter object, which stores the frequency of digits. This requires at most 10 space because there are only 10 possible digits. Additionally, the string representation of the number requires d space, where d is the number of digits. Therefore, the space complexity of is_numerically_balanced is OD. For next beautiful number, the space usage is minimal beyond the is_numerically_balanced function. The variable current is a single integer, so it uses 1 space. Combining both components, the overall space complexity is dominated by is_numerically_balanced, resulting in OD. When comparing this approach to other methods, it's clear that the solution is essentially a brute force approach. It checks each number linearly until it identifies the next numerically balanced number. Since there is no optimization to skip non-candidates, the worst-case time complexity remains 10 to the power of k asterisk k. In the best case, where n+1 is already numerically balanced, the function terminates immediately, with a time complexity of k. On average, the function will test a few numbers before finding the next balanced number, leading to a complexity of 10 to the power of k asterisk k. In the worst case, where the next balanced number is far from n, the function iterates through all numbers in the range, yielding the same 10 to the power of k asterisk k complexity. From a mathematical perspective, converting a number to a string and counting digit frequencies are linear in the number of digits, which explains the OD complexity of is_numerically_balanced. The iterative search in next beautiful number scales exponentially with the number of digits due to the size of the search space, resulting in the overall 10 to the power of k asterisk k time complexity. Space complexity remains linear in the number of digits due to the temporary storage in is_numerically_balanced, keeping it at OD. One common mistake when solving this problem is misunderstanding what a numerically balanced number actually means. Some people think the digits must appear consecutively or in sorted order. However, the correct definition is that for each digit d in the number, the digit must occur exactly d times. For example, the number 122 is numerically balanced because the digit 1 appears once and the digit 2 appears twice. To avoid this mistake, it's important to carefully analyze the problem statement and examples to clarify edge cases. Another frequent pitfall is starting the search from n itself instead of n+1. If the problem asks for the next numerically balanced number, beginning from n can lead to returning the current number when it's already balanced. To fix this, always increment n before starting the search. Lastly, some solutions rely on inefficient brute force techniques, which can be problematic for large values of n, such as when n is up to 10 to the power of 6. To address this, you should add constraints to your approach, such as eliminating candidates with digits larger than their frequency early on. This can save significant computational time. Overcomplicating frequency counting is another common mistake. Some solutions use nested loops or manually count digits, which makes the code harder to read and more prone to errors. Instead, you can leverage efficient data structures like Python's collections counter or similar utilities for straightforward and reliable digit frequency tracking. Additionally, edge cases like transitioning between digit lengths are often overlooked. For example, numbers like 99 or 1000 can cause issues if the solution doesn't account for boundary conditions. These transitions require careful handling, as the digit composition changes significantly. Testing edge cases thoroughly and ensuring your solution is robust across different inputs can help mitigate these issues. To perform well in interviews, it's helpful to focus on key insights about this problem. First, recognize that at its core, this is a digit frequency analysis problem. Efficient solutions capitalize on patterns in how digits and their counts interact, rather than relying on exhaustive enumeration. Optimization is critical. Once you have a brute force solution, narrow the search space by skipping invalid candidates, such as numbers with digits that exceed their frequency limits or numbers that include zeros unnecessarily. Structuring your solution with modular thinking is also helpful. For instance, using helper functions like is_balanced can make your approach cleaner, easier to debug, and more intuitive to explain. Finally, communication is key during interviews. When asked to validate a numerically balanced number, walk through examples step by step and articulate your thought process clearly. This shows both your understanding of the problem and your ability to communicate effectively. This problem shares similarities with other LeetCode questions, making it useful to study related problems. For example, LeetCode 202, happy number, involves an iterative process where recognizing patterns is critical to avoid infinite loops. LeetCode 728, self-dividing numbers, requires digit-wise checks for specific properties, much like this problem. LeetCode 1217, minimum cost to move chips to the same position, emphasizes the importance of recognizing patterns to minimize brute force computations, which is also crucial here. Lastly, LeetCode 1399, count largest group, directly involves digit frequency analysis, though in a different context. Exploring these related problems can deepen your understanding of digit-based algorithms and help you develop transferable problem-solving strategies. There are several alternative approaches to solving this problem, each with its own trade-offs. An optimized brute force method skips invalid candidates early by analyzing digit constraints. For example, you can immediately disregard numbers with digits that exceed their possible frequency. This approach is easier to implement but can still be slow for very large n. Another option is backtracking. By generating all possible numerically balanced numbers within a reasonable range, you can avoid unnecessary computations. This method is often faster for smaller constraints but requires a more complex implementation. Finally, pre-computing all numerically balanced numbers up to 10 to the power of 6 and storing them allows you to use binary search to quickly find the next number. While this is highly efficient for repeated queries, it does require additional memory. Choosing the best approach depends on the constraints and requirements of the problem scenario. Thank you for watching. Today, we tackled the next greater numerically balanced number problem, explored its brute force solution, and discussed key concepts. Remember, practice makes perfect, so keep challenging yourself with similar problems. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!